Alright, I wanted to go through a practice problem to help you guys prepare for test number 3. This is problem number 17 from chapter 9. And we're talking about dropping a tennis ball on top of a basketball, letting it hit the ground, it elastically colliding with the ground, and of course the basketball is just going to launch the tennis ball, and that's the third frame. If you've never tried this, it's really fun. You just kind of drop them vertically, right next to each other, and the basketball will lose a lot of energy and just launch the tennis ball up. So I actually just made a video about this whole thing, and I tried to wade through the math, and I didn't get it right, so I needed to start over again. So unfortunately, I'm not going to be working with the decimals and the quadratic. I'll show you how to set it up, and then I'll let you guys solve it, and if you have any questions, please email me. Because I've already solved it once, I don't want to do it again. So the mass of the tennis ball here is 0.057 kg. Mass of the basketball is 0.59 kg. We dropped this from a height of 1.2 meters. And so it's curious about what the velocity of the basketball is when it hits the ground. Well, we could just go ahead and calculate the sum of energy initial equals the sum of energy final. So initially we start at rest. So all we have is gravitational potential energy. That's m of the basketball times gh is equal to the kinetic energy at the end, because I chose my potential equals 0 line here. So at the end I just have kinetics. So that's 1/2 m basketball times v final squared. Now I just want to point out that the masses cancel here, which makes sense because on Earth it doesn't matter how heavy something is that you drop, it's going to fall at the same acceleration. So in fact, the velocity the basketball will reach in this, from going from here to there, will be the same amount of velocity that the tennis ball will reach. So the system will reach that velocity together. And if you'll see here, we're solving for v final. Multiply over the 2 gh under the root. And so part A comes pretty quickly. 2 times 9.8 times our height of 1.2 gives us a v final of 4.85 meters per second. So this is part A. Then the next part, we're going to have to kind of move from one frame to another. The problem specifically tells us that right after the basketball hits the ground, that it instantaneously switches velocity upwards. So we know that the velocity of the basketball right after impact of the ground is the 4.85 meters per second in the upwards direction. And so let's go ahead and draw a diagram here. So it tells us that the basketball immediately flips its velocity. So here's the basketball. It's flipped its velocity upwards. But the tennis ball, which is on top of it, it's still touching it, is traveling downward at that same velocity of 4.85 meters per second. And so they're going to collide. And the problem tells us it's a perfectly elastic collision, which means that we have two tools that we can use. If you've seen the other videos or heard this in the lecture, you can now use conservation of energy and conservation of momentum with elastic collisions. You cannot use conservation of energy with inelastic collisions. For inelastic, you can really only use momentum with certainty. But in this case, we can use both, and we'll need to use both. So the first equation we'll do here is energy. So you'll see at this point, right before they collide, and then an instant later, the tennis ball will have some final velocity. I'm just going to call it v of tennis ball. And the basketball will have some small upward velocity, v sub b. So we know that the energy must be conserved because there's an elastic collision here. So energy initial equals energy final. So the initial energy here, thankfully energy is a scalar, so we don't need to worry about directionality. So we start with the kinetic energy of the basketball, 1/2 mv times vf squared, because it's going at that final velocity, 4.85 meters per second, an instant before they collide, plus the kinetic energy of the tennis ball 1/2 mt v final squared, because the tennis ball is also traveling at that final velocity downwards. Then on the other side, we have kinetic energy with both of them. Kinetic energy of the basketball 1/2 mb times vb squared. That's my final velocity for the basketball. And then I have plus 1/2 tennis ball's kinetic energy, mt, times vt squared. Alright, so that's my first equation. It turns out that I know my masses, I know my VFs, I solved that in the last problem. So my two unknowns in this equation end up being VB and VT. And I can't solve for two unknowns with one equation, so this is why it's useful that we can use conservation of momentum here, because that's where my next equation is going to come from. Alright, so sum of momentum initial equals sum of momentum final, remembering that momentum is a vector and we have to add it as such. So our initial momentum, let's go ahead and say that this is up. So initially our basketball has positive momentum. Remember, momentum is mv. So that's m of the basketball times v final, because at that point in time they're both traveling opposite each other with v final, minus mt, mass of the tennis ball, because it's going downwards, times mf, which is the speed at which the tennis ball is going downwards, equals final is, we're going to look in this frame. So final, we have both of them going upwards. We have mb times vb, the momentum of the basketball after the collision, and then another positive value, mt vt, which is the mass and the velocity of the tennis ball immediately after the collision. Now I wanted to point out, just on this conservation of energy, the reason why there was no potential energy due to gravity here is because I am evaluating this collision like an instant before and an instant afterwards. And so the collision, an instant before, is still on the ground, and an instant after, it's pretty much still on the ground, so we got to ignore potential energy here. So here's our two equations that we get from summing energies and summing momentums. It's looking like I'm actually going to have to solve this all the way through, because the question asks, how high does the tennis ball go once it's at rest after it's gone up to its maximum height. So I'm just going to go ahead and plug in everything I know. I'm going to go through here and show you everything I don't know. I don't know these things. So I'm just going to go ahead and plug these in. So this ends up giving me 2.586 equals 0.59 VB plus 0.057 VT. That's for this equation. Let's see what the energy one gives us. The energy one ends up giving us, because this side is just a number, right? I end up with 7, actually let me do it this way, I end up with 15.22 equals 0.59 times the velocity of the basketball squared plus the mass of the tennis ball, 0.057 times the velocity of the tennis ball squared. Well, that was nice. I actually tried to walk through all the calculations last time and ended up screwing it up, wasting about 20 minutes of my time. So I know these ones are correct because I had calculated them before I started shooting. So I've got two equations now, two unknowns. I'm going to go ahead and solve, because I know I don't care much about the basketball. I want to know how high the tennis ball goes. And in order for me to know that, I have to know the velocity at which the tennis ball leaves. So I want to know the velocity of the tennis ball. So I'm going to solve for the velocity of the basketball in terms of the velocity of the tennis ball. And so I'll subtract that over and end up with 0.057 VT equals 2.586 minus 0.59 VB. Then I'll divide everything by 0.057. 0.057 ends up giving me 45.37. 0.59 divided by 0.057 ends up giving me 10.35 VB. Or I'm sorry, I wanted to solve for VB in terms of VT. Let's go back to the sheet. Alright, so I'm just going to divide everything through by 0.59. Okay, so when I solve for VB, I end up with VB equals 4.383 minus 0.0966. Alright, so now I'm going to go ahead and plug that into this equation right here, our energy equation. I'm going to make some room up here. Alright, so I'm going to plug this into the energy equation. And what I end up getting, I'm not even going to do it. I'm just not going to do it. I'm not going to screw up a second video. So what I end up getting when I do all that is I end up with a quadratic equation that is 0.0625 V of the tennis ball squared minus 0.5 V of the tennis ball minus 3.9 equals 0. I plug that into my quadratic formula and I get two possible velocities of the tennis ball. One of them is 12.85 meters per second, and one of them is negative 4.856 meters per second. And in physics, if we set up everything right, we can go ahead and neglect the negative number. So now we know the final velocity after the collision of the tennis ball. I'm sorry I didn't go through all the calculations. Hopefully you'll be able to just do the substitutions in quadratic equation necessary to find this solution. If not, send me an email and I'll shoot you the work through. So now we pretty much know all that we need to answer the question about how high does the tennis ball go. So we know that when the tennis ball starts out, it's on the ground, but going upwards at 12.85 meters per second. We'll go ahead and use conservation of energy again. Sum of energies initial equals sum of energies final. So initially all we have is the 1/2 mvt squared, because we know that we're pretty much at ground level. We're at our potential equals 0 line for gravity. And then we know that once we finish, we're looking for maximum height. So that means the ball has come to a complete dead stop in midair, which means that all we have left is its gravitational potential energy, which is mgh. The m's cancel out. We know that Vt is 12.85. Square that. Divide it by g to solve for height. And what I end up getting is 8.42 meters. Let's see if that agrees. Yep, that seems like a reasonable answer. So that is the maximum height that the tennis ball will reach, which is quite astounding when you consider that the thing started at being dropped from 1.2 meters. So the fact that the basketball transferred so much energy to the tennis ball as to launch it 7 times higher than it initially started is pretty impressive. Alright, I hope this was helpful, and I'll see you next video.